Hi guys. All right, let's work through a solution for the C-sizer exercise from last week. In the CS61 exercises fundamentals 2x directory, you'll find a program skeleton called C-sizer.c. Complete this program. C-sizer should parse C type specifications from strings and output the sizes of the corresponding types as the compiler for x86-64 would compute. Type spec is built from these characters. C is char, S is short, I is int, L is long, F is float, D is double, P is a pointer. And a spec with more than one character describes the C struct with those components, like this, char, int, char, float. Next. All right, a bunch more text here. Already getting bored. Let's take a look at the code. The same text. This time it's a little bit more compact. And what is this? We have some examples. Spec size C should return 1 since size of char equals 1. Spec size CIC should return 12 since the size of that struct, char int char, equals 12. If you don't know why that equals 12, we'll talk about that in a minute. But it seems like this is a good place to start. When we have some examples, we can make our code produce those examples. All right, so how does this code actually work? There's our main function. Looks like the main goes over the list of the program's arguments, starting with argument number 1, which is the first real argument. Argument 0 is the name of the actual program that's running. Then it goes up to the last argument, which is argc -1. And for each one, we print the result of calling spec size on the argument, and then we print the argument. And spec size, this is the function, this is the core of our work, takes in a string and returns an size t result. The size t being the type of sizes. It's an unsigned integer type. Okay, so if I actually run this, how's that going to work? Let's, well, if we run no arguments, does nothing. Give it a C, print 0, S, 0, I, 0. Now, something I want to point out here, notice this command line has some ampersands in it, right there. Make and C-sizer. What does that do? So this is a way of constructing a single command that runs multiple commands. So the single command line make and C-sizer CSI runs make, checks whether make succeeds, and if and only if it succeeds, it goes on to run C-sizer. So this is really useful because first of all, it runs both of them in the normal case. But if there's some error that we might need to take care of, like somebody has written error in the middle of our code, the make will fail and we don't actually go ahead to run the older version of C-sizer, okay? So these kinds of little command line changes will really help you be more efficient as you work on the command line. Let's get rid of that error and make our spec size. We want, our first goal is to make spec size of C return 1. Well, that's pretty easy. C-sizer of C returns 1. Great. C-sizer of S and I also return 1. Clearly, we're going to have to fix that next. In order to actually analyze the string, we need to analyze the string argument. C strings are represented as arrays of characters. In C, arrays and pointers are fungible. We can take an array of characters and treat it like a pointer. And it's very idiomatic in C to treat character arrays especially as pointers, const char stars, usually, not always const, so that we can walk through the array one character at a time by moving the pointer around. We'll see an example of that right away. But first, let's treat this character string as an array of characters. So if we're trying to figure out whether the first character is C, that's pretty simple. Right, first character is C, return 1. Otherwise, let's return 0. Okay, we have one correct example here. The character C returns 1, as we expect. Now, what about all of these other types? S, I, L, F, D, P. Well, these are supposed to return sizes. So maybe the best way to write this is with sizes. Is the size of char 1? Well, it always is. Let's double check. It is in this case too. For the other types, I just copy the portion of the code that I've already got correct and change the characters and the types. Okay, let's just check our work. Great, CSIs, we got that. CSIL, good. An unknown character is going to get 0, that's fine. We haven't been told what to do with unknown characters. In fact, I think the spec says that unknown characters, you can do whatever you want. The behavior is undefined. But we have some other non-undefined characters we need to work out. F is float. D is double. And P is the size of a pointer type. I'm using void star there. On all the machines that matter now, all pointers are the same size. So we can just use whatever pointer size we want to represent the size of a pointer type. If I now run all of the single character specs, I have the right results for every single character spec. Great. So let's take this and make it a function. Since single character spec seems like it might be a useful subroutine to use as part of the code for a multi-character spec. So I'll just call that spec size 1, and it will take a char argument, not a char array, because this spec size 1 is meant only for single character specs. So I just changed the spec string reference to the spec character reference. And now spec size will return spec size 1 of the first character in the spec. Nothing should have changed. Looks like nothing did change. But, so we've already done one of our useful steps on the way to a fully working C-sizer, which is single character specs. But of course, multi-character specs don't work. We get 1 for each of these sizes. You might think that this would be good enough. Well, you probably wouldn't think this. So this takes the length of the specification and multiplies it by the size of the first character in the specification. Well, that doesn't work. That is not correct, but it works for the examples I've given so far. And in fact, this example works for any spec that has the same character repeated 0 or more times. Let's try a 0 length spec. That's a string with 0 characters in it. You have to give the quotes so that the shell, which is the program parsing this command line, knows that there's an actual argument there. Okay, all those work. This one doesn't. Or does it? In fact, that one also gives the correct answer. IC works, CI doesn't. Why not? Let's focus in on these two specs, IC and CI. What is the correct size for a struct that contains an integer and then a character? Well, it's got to be at least 5, right? Because we know that C objects don't overlap, and we have a 4-byte object, an int, and a 1-byte object, a char. They're being packed into a struct together, so they have the size of the struct is always at least as big as the sum of the sizes of the components. 4 plus 1 is 5. The result has got to be at least 5. Okay, so we know 2 is wrong. Where do we get 8? Well, this is from alignment issues. The alignment of fundamental types in C is often, not always, but it's often equal to the size of the type. And for int, that's actually true. Using the C extension underscore underscore align of underscore underscore, which reports the alignment of a fundamental type. So ints need to be aligned on a 4-byte boundary. That means that if an int is placed in memory, it will be placed so that its first byte, the address of that first byte, is evenly divisible by 4. The alignment of a structure equals the maximum of the alignments of any of the parts. So that says that the alignment of a structure containing an int is going to be at least 4. The size of a structure is always a multiple of the alignment. So that means that the size of this structure, IC, is going to be a multiple of 4. So what's the smallest multiple of 4 that's at least 8, that's at least 5? The answer is 8. So the correct size for IC is 8. That explains that. The same logic applies to CI. And in both of these cases, what we're going to see is a little bit of padding. If I sort of imagined, padding is space inside of a structure that doesn't correspond to any of the structure's components. If we took a struct that contained a char and then an int, here's how we would lay that out. First, there would be 1 byte corresponding to the character. Now we want to find a space suitable for the integer. But that space suitable for the integer has to be aligned on a 4-byte boundary. We can't necessarily say that the 4-byte boundary will come next because the alignment rules don't work out. Remember, the alignment of the struct is always the maximum of the alignment of the components. So the maximum of the alignment of the components here is 4. So the alignment of the struct is 4. That means that the struct's first byte is on a multiple of 4. So that A character is occurring at a multiple of 4. We now need to add padding to get to the first character, the first address that's a multiple of 4 after the address of A. That's 3 bytes of padding. Now we've gotten to the next multiple of 4, and we can lay out B. So I'll write that this way. And that is our structure. Okay? So we add padding to pad out to the nearest multiple of the alignment of the next component of the structure. Let's see how we can program that. Or let's try to program that first. So first of all, what is the alignment of a type? Well, it turns out that there's a special function that returns us the alignment of a type. The name of that function is __ align of. There's a hint about it in the problem description. If you want to know how something works, you might as well just type it into Google. The keyword align of allows you to inquire about how an object is aligned, or the minimum alignment usually required by the type. Well, that's convenient. It's exactly what we want. There's my trash. What I'm going to do now is I'm going to copy my spec size function, and I'm going to instead create a spec align function, which returns the alignment of each of these fundamental characters that can make up a spec. So we just change the word size of to align of. Okay, so spec align 1 will now return the alignment of a particular character. So how can we find the alignment of a structure? Well, the alignment of a structure is the maximum of the alignments of any of the characters. In fact, the alignment of a structure is the least common multiple of the alignments of any of its components. But on normal, basically to make things easier to deal with, on normal machines, all of the alignments are powers of 2. So the least common multiple of a set of alignments is the same as the largest of the set of alignments, because every power of 2 divides evenly all larger powers of 2. So we write a function that returns the alignment of a specification. We've got a function specAlign1 that returns the alignment of a single character. So how do we calculate the alignment of a full spec with multiple characters? Let's start out with the current alignment and set that to the smallest alignment possible, which is 1. Everything is aligned on a byte. Now we need to loop over the characters in the string. There's many different ways to write a loop over characters in a string, but the one way to do it would be to use an index. Let's leave that out for a second. And then inside this loop, we would refer to spec bracket I as the current location, as the current character. How do we know when the string is over? We could do this. Compare against the length of the string. It's much more efficient to just check for the 0 character. Exact same effect, but much faster because we're not calling that Stirling function multiple times. This is an O of n algorithm, whereas the version that checks Stirling every time is an O of n squared algorithm, because Stirling itself takes O of n time if a string has length n. Okay, so spec I not equal to 0. But it's more idiomatic in C. In a situation like this, what we'll often see is an alternate version of this loop, which actually just modifies spec. And inside the body of this loop, we refer to star spec as the current character. If you're not comfortable with pointers, this is going to be a little surprising. We'll address that in another video, perhaps, or come and talk to us at office hours. So let's write it this way, the version with pointers rather than the version with arrays. Okay, so for each character in the spec, let's get the alignment of that character using our specalign1 function. And then say curalign is the max of the curalign and the new alignment. So if A is greater than curalign, curalign equals A. Return curalign. Okay, so what we expect this function to do is return the alignment of a structure, which is the maximum of the alignments of its components. I'm going to get rid of this version of spec size, and just to show you how this works and to check that I did it correctly, I'm going to change the spec size function to just return specalign. Both of those structures have alignment 4, which is good. The alignment of a long is 8, so any structure containing an along should also have alignment 8, and it does. Okay? So now we know what the alignment is of a structure. So if we know the alignment is what the alignment is of the structure, we can figure out the current position of where we're laying out the next character in the struct relative to the alignment. Now it turns out you don't even need to know the alignment of the whole structure in advance, but we'll see that in a minute. So, structure alignment is the spec alignment of the spec. Now, what I want to do is actually lay out the components of the structure in order to create to calculate its final size. So we'll use a loop of the same form. And what I suggest here is that we think about how the compiler lays out objects. So the compiler lays out objects in the same way that we did when we were doing a little diagram a little bit earlier with the CI spec. The next character goes at the next element goes at the earliest available position after potentially adding some padding to bring that element into alignment. So what we need to do in order to figure out the current position is have a running position. Let's call that pause. So we're about to lay out a new element of the structure at this position. So first we want to know how much padding to add. For that, we need the alignment of the current character. So when do we need padding? We need padding when the current character is not aligned properly. How do we know when it's aligned properly? It's aligned properly when the position is a multiple of the alignment. So if pause mod alignment equals 0, then we're okay. Don't need padding. Otherwise, well, what do? We need to add some padding to the structure. How do we add padding? We add a byte to the structure. What does that look like? Incrementing pause. So otherwise we increment pause. Okay, does this work? This does not work because we might need to add more than one byte of padding. But if we think about this and just tweak it a little bit, we'll see that we can fix it. We stop adding padding when the position mod the alignment is 0. That means that we keep adding padding until the position of the mod the alignment equals 0. So while the position mod the alignment is not 0, add a byte of padding. Now it turns out that this is a while loop. Can we get rid of this while loop and make it a single expression? Yes, you can. You have to figure out how. Okay, so at this point, we've added the padding. We need to add the actual component. And that is easy too, because we have our lovely little spec_size1 function that tells us the size of a given component. Are we done? Well, let's see. We're not using this struct alignment variable that we had before. Okay, I can't even think about whether that answer is right. But let's look at our single characters. Are they right? Those all look good. What about our multiple versions of the same character? That looks good too. 3 characters, 4 characters, 5 characters. Great. What about CI and IC? CI looks great. We've added the padding properly. But IC does not look great. What's wrong? We haven't added the padding for the structure as a whole, the padding that will bring the entire structure up to the required alignment. The size of a structure is always a multiple of its alignment. That's what we need struct alignment for. We know how to add padding. While pause mod struct alignment is not equal to 0 plus plus pause. Ooh, I seem to have messed up. This is one of the many problems that can happen when you modify a variable. You may not have noticed this, but earlier we had struct alignment up here at the beginning of the function, and that calculated the alignment for the input specification, spec. Then, in an attempt to make things cleaner, I moved that initializer down here, where we initialize struct alignment from spec. That would work great, except, of course, this loop modifies spec. When the loop is empty, the spec pointer is pointing to an empty string, so of course the struct alignment is 1. So let's just leave this where it was. Yes, CI is 8, IC is 8, CIC is 12, just as the C-sizer code told us it should be. Now let's try this example, because this example seems like it might be pretty hard. CCI CFP 24. We now have a correct C-sizer.